Hello guys, hope you're doing well and welcome to the new chapter of electronics actually. At this point we are going to talk about the next part that we somehow left uncompleted last time. So we talked about how we can convert the nonlinear component diode to the linear component. Why we're doing that? Because if we could achieve this fact, we could use that one or any other kind of linearization method that we have, right? It's about the KCL, KVL, everything related to that. If I can do something with the diode itself, which is a nonlinear component, and make it to the linear component, which is a resistor, I can do all of that. So we talked about a little bit of about the step number 1 to number 4. So we are talking about the phases at this point right now, which is some kind of the same. And we are trying to solve a couple of different questions to see that what would happen if we consider the bias point, the voltage and the current. We just consider the bias point as a reference, then we will move on. And what would happen if we just inject the AC or DC or maybe the combination of those, and what we should do at the end to have all of them at the same step. Without further ado, let's talk about it. So as I just talked about that one, the very phase 1 is about the initialization. It means that right now, what I have to find the DC bias itself. So as you can see over here, what I do have some kind of diode, and I would like to make it a linear. Why making a linear means that instead of just diode itself, I would like to make what? I would like to make a resistor. As we all know, we do have a formula for that. The resistance, the RD, is VT divided by ID. So if we assume that ID, or the current that goes through some kind of diode, is 1 milliamp, and the thermal voltage, which is some kind of a very common voltage for it's related to each diode, but right now we just assume it as 25 millivolts. If I assume those two, I can say that my RD is equals to VT divided by ID, so RD is going to be 25. By the way, at the room temperature, right now I'm going to show it to you. At the room temperature, the thermal voltage is the constant that defines the relationship. Resistance is inversely proportional to bias current, as we just saw. So VT, most of the time, most of the question considered as 25 millivolt. We do have the ID and we can find the RD. That was very beginning of the phase that we would like to some kind of replace the nonlinear component with the linear one. Then we do have the conductance as the primary driver. So if you guys remember, at the very beginning of the point, we define this guy. We define the conductance, that's the unit measurement is Siemens. So the conductance is the reciprocal of the resistance, and the formula is I divided by V. Imagine that I do have a condition that my ID is 2 milliamp, and the step number 1 that the question asks to find the conductance, then find the resistance. So obviously the only thing you have to do is just divide ID by VT. ID is 2 milliamp and VT is most of the time 25 millivolts, so you've all found the GD itself is in the Siemens, by the way. Then by finding the reciprocal for that, you can find the RD. So most of the time we just need the RD itself, but just in case if the question asks you, I can also find the GD itself. Then we do have the static loop. At this point, we are still working on the initial phase, and we would like to find what? We would like to find the ID itself. At some point, the question would give it to us, but we would like to find out. What we would do at this time, just forget about converting a nonlinear to linear. As you guys know, diode acting as a switch. If I can give this guy enough voltage, most of the time is 0.7 volts, sometimes it's 1.3, sometimes 1.7. It depends on your LED or your component itself. This guy, instead of just acting as some kind of open circuit or any other or a nonlinear component for you, this guy can act as a wire. So that is a good thing. So if I assume that at this case, I do have the diode, and this diode would be activated at 0.7 volt, and I know that I do have enough voltage to activate this one. Right now, we would like to find a couple of things. The very first thing that we would like to find is the ID. How we can find ID? As you guys know, the current that goes through the diode is the same as the current that goes through the resistance. So if I can find the V divided by R for this one, I can find the ID itself. Obviously, the positive side of the voltage, which is over here, is connected directly to 5 volt, and the negative part is connected to what? To the VD, or the amount of voltage drop that happens because of the diode itself. So 5 subtracted by 0.7 divided divided by R, or the 1K, is going to give me ID. And if you find that at the very end of the day, you do have your ID. Since you have the ID, you know that you can find the RD itself. So that is the point. That is actually the time that we are going to use the DC results, that was the ID itself, and use it in AC parameter, because right now we can convert my ID by using the VT and ID to RD itself. So if the question asks to find the RD, or how I can replicate or some kind of replace my nonlinear thing, linear thing, you do have the ID, you do have the VT, you can do that. 25 divided by 4.3, so you do have 5.8. Right now we can use it in AC analysis. So let's go to the phase 2. At the phase 2, as I just told you, we do have the RD. So at this guy, we are going to talk about the linearization, the signal conversion. Imagine I'm looking at the point that my ID is 0.5 milliamp. After I found all of this, some kind of related thing, I found that my ID is that one. So the very first step that we have to do, as I just told you, we have to find what? We have to find the RD. Then using that, we are going to find ID based on the Ohm's law, not in DC mode, but in AC mode. So I do have the 10 millivolts. If I assume that this is going to be RMS value of my input voltage, as you can see, it's AC. So VDI, there is maximum or RMS. And then I'm going to find how much current actually goes that. Because in previous part, as you just saw, we were only talking about the DC. But what would happen if we do have AC at this case? So we have to some kind of flow. So my ID, its AC part, is going to be what? Most of the time they show it with I small. But this guy is the capital one. So we do have it as VD divided by ID. So what was the VD itself? VD assume that it is the 10 millivolts, not assume actually, because we already found it over here. The question gave it to us. VD divided by RD that we just found from our some kind of resistance, the formula related to that. So you'd have it as 0.2 milliamp. So remember, we use the simple Ohm's law, V is equals RI, to analyze a highly nonlinear device. This is valid only for small signals. As you can see, the signal is 10 millivolt. I can use it with that one, but if your signal is big, for example 10-20 volt, we cannot do that. So another thing, or another mathematical origin of this linearization is related to IV. If you guys remember, right now I do have the VD and I do have the ID. So this is related to the voltage and current, or relationship between the voltage and current. But you guys remember, we found the bias point, and this bias point is going to help us. By finding the slope of this bias point, we do have the GD, or we can use it in order to find the RD itself. So let's talk about this, some kind of calculus. Imagine that I do have a case that my ID equals to what? My ID equals to IS times exponent of VD divided by VT. This is the formula that we talked about it last time. So we are going to talk about the differentiation. The GD is DI divided by DV, sorry. So as you guys know about that, right? Rise over run. So we are going to evaluate it at the Q point. D over DV, or based on this current, and there's some kind of divided by DV, or the derivative of ID based on the V is going to give you this formula itself. 1 over VT times IS times exponent of VD divided by VT itself. So we are going to use the substitution. It means that when you have the ID, then we are going to find the GD itself, right? So the GD is going to be 1 milliamp divided by 25 millivolts. We do have the VT, we have the ID at this point, we found it, so we do have it as 0.04 Siemens, or we do have it, we can't just find the RD. So at this case, we do have a small signal analysis. It's going to be simply the first direction. The slope of the tangent line is your conductance. We use that one, either we can just use the calculation, or just you can use this one in order to find that one. Most of the time we just use the calculation method. I mean, not very working out this some kind of the calculus and formula part, because it would be solid in advance. Then we do AC equivalent circuit. It means that still at the phase 2, and we would like to build the AC equivalent. As we all know, right now we're dealing with the AC part. Since I do have an AC part, I need to find the resistance. The total resistance is the combination of this resistance. Why resistance? Because we know we could just convert the nonlinear component to linear component. And more resistance that we have. So what we should do in order to find that, first of all, we have to get rid of the AC signal. Make it as a short circuit. If it was a voltage source, short circuit. If it was a current source, open circuit. And we just found the RD. Right? From the previous part. I do have 50 ohm and I do have a 1000 for my normal resistance. If I add them up, I do have around 1050 ohm. That's how I can find my R. Then we are talking about the signal distribution via voltage division. We can use that at this point. So right now I do have my input voltage, for instance, as 100 millivolt. Then I do have my resistance at 1000 and I do have my RD as 50. So we are going to use that in order to find a VD. V in is 100, R is this one, and RD is this one. So I can use what? I can the rule, because right now I'm talking about what? Condition. I still can do that. So if you use this formula itself based on the calculation, your VD would be something around 4.76 millivolt. Right now, we're just talking about the DC, but since it's a small signal, you still can talk about the AC itself. So let's see what would happen actually if we change the bias. Imagine that we do have two cases. At the case number 1, my ID is going to be 1 milliamp, and the case number 2, my ID is going to be 2 milliamp. So if ID is 1 milliamp, based on the formula that we have, our RD is going to be 25 ohm. But if we are talking about the 2 milliamp and ID is going to be 25 millivolt divided by 2 milliamp, my RD is going to be 12.5. What we just saw, we saw that inverse proportionality. It means that doubling the bias current strictly cuts the dynamic resistance in half. That's why it is important. Even the small changes in your bias condition or consideration is going to lead you to make your RD, which we assume that as our linear resistance in half itself. Phase number 3, what would happen if we do have the integrated system? It means that I do have the linear system, then my diode is going to be connected to that. As you guys know, each linear system can be replaced by is Thevenin or Norton. The Thevenin voltage at this point is 3, and the Thevenin resistance is going to be 2. So right now, let's talk about the DC analysis. In DC analysis, I would like to find my ID, because after that, by finding the ID is going to help me to find my RD in AC analysis. So the DC as an analysis, the ID is simple. VT subtracted by V diode, we just saying that as a passing voltage by 0.7 volt. 3 subtracted by 0.7 divided by R Thevenin is going to be 1.15 milliamp. Then we do have the step number 2 using the AC parameter extraction. So we do have IT is equals to VT divided by, the RD is going to be VT divided by ID. Since I do have the VT, most of the time we consider 25 millivolt, I just found the ID, I can I can find my RD and replace it. Instead of just using this diode, I can replace it with a resistance itself. So what about the voltage gain? This voltage gain is that's a voltage divider thing. It's not going to be some kind of the voltage gain most of the time is going to be at the point that you do have the op amp, but we also can talk about over here. Imagine that I do have a case. My RD is 25, my R is 1K, and then a question asks how much is V out divided by V in, or how much is the gain. So we do have a formula for that, right? Which means that V out equals the V in times your R out divided by R out plus what? Plus your RD itself, right? We would like to find this gain related to what? Related to our resistance. So we can have this formula. I can move the Vn over here, and V out divided by Vn is going to be that. So R is going to be 1000 divided by 1000 plus 25. We found it, and AV is going to be 976. What does it say? It means that the gain is slightly less than 1, and the diode acts as a very, very, very small insertion loss. So we don't have to worry that much if we are dealing with a resistance or high resistance beside that. Another thing that we can see is about the superposition of signals. So what does it mean? Imagine that I do have a case that in my DC bias, ID is 1 milliamp. So obviously I can use that one in order to find the RD itself. And in AC simulation, my current is 20 microamp. So the problem is find AC voltage magnitude or VAC. As you guys know, So V equals R times I. It doesn't matter what AC or DC, all the time it works, especially when they're talking about linear condition. So going to be my AC voltage is R, that I found it from the DC bias, that I still can use it, times the current that I had at AC. So it's going to be what? It's going to be 0.5 millivolts. What does that? Imagine that this some kind of 120 microamp was the maximum current. Right now, we just found the maximum voltage related to some kind of the system, related to our some kind of circuit itself. And as you guys know, V equals Vm sine of omega t plus what? Plus phi 0 plus 30 0, whatever. So it means that right now I can write down my AC voltage as formula like this. And why we are going to add it with 0.7 volts? Because 0.7 volt was about the DC voltage, or the amount of voltage actually your some kind of diode is going to have, or this is the cost for your diode to act normally or to act in a linear condition part. So it means that my voltage source, which was a combination of AC plus DC, has what? Has a diode, and plus maybe, or has a diode itself, and plus maybe other part. But since we are talking about this voltage, we don't care about that, but still we care about the 0.7 volt DC of the diode itself, and the wiggle or some kind of the AC part that we do have it over here because of the 20 microamp. Right now, I'm not sure what is happening inside of that. The only thing that I know is about the current, which is totally fine for me. Then we do have the parallel equivalent resistor. This is a very, very simple question. Imagine that you do have a condition like that, and after question would just simply ask, what is the parallel resistance of these two, a diode and a resistor? As you guys know, in some kind of the AC condition, I can consider that diode as a resistance, nonlinear part to the linear part. So for instance, this part is 40, just find 40 and 96. As you guys know, since R is way, way bigger than 40, probably your final resistance is going to be somehow very close. To your small resistance, which we divided at 38.4. So quantifying that would happen if temperature would change and my some kind of small current, the I, would change from 1 milliamp to 1.2 milliamp. So the RD1 or the RD at the beginning of the point was what? Was VT divided by my first current, 25. And R2 is going to be VT again divided by its new current, this one. So you can see that what happened at this point. Or we can say that a 20% increase in current leads to a 60.7% decrease in the resistance itself. A small shift significantly altered the impedance itself. And finally, the complete analysis of the workflow. We talked about it in order to do what? In order to reach to this section. So at the very beginning of the point, we do have the DC analysis. Why we use this DC analysis? Because we have to find the ID. Then by using the ID and VT, we can find the RD itself. Then we do have the AC current. Right now at the beginning of the part, we found the DC current. For the AC current, we can do what? We can find Vn, obviously is the AC voltage, divided R plus RD. What is R? It's just a normal resistance that we have, and RD is a resistance that we found. And finally, your ID is going to be this one. So what is the AC voltage? AC voltage is the multiplication of ID, which was about the AC current times the RD itself. So you do have it as this one, and if you want, you can convert it to the normal format that we already know. So what happened at this chapter and the previous parts, by the way, we were trying to talk about the RD, or we tried to talk about the nonlinear component and how we can convert it to the linear component, then use it in our calculation. I tried to show you a couple of examples that what would happen and what would happen if we change our bias. That's why that specific point is so important. If you just change it just a little bit, your RD would be changed and everything would be changed. I also show you that how you can use it in order to find your AC source, what was the combination of AC and DC, and so on and so forth. So I believe that's more than enough for you right now to just know what is happening inside the diode itself. By the way, this is electronics 101. We won't want to talk about it in detail. As you're dealing with the derivatives, what would happen if you use all of those scary formulas? No, don't worry about it. Try to some kind of understand the whole concept. That would be way better, because in the future, we are going to use the diode and this concept a lot. So if you have any question, please comment me down below. I would be more than happy to answer that. My name is Mahmoud Kesari. Have a super great day, night, whatever. See you around.